Every single calculation in trigonometry relies entirely on one specific fundamental geometric system, the structural foundation of the right-angled triangle. The rules governing this shape are anchored by a single feature, a perfect 90-degree angle. Positioned at that 90-degree corner, looking straight across the internal space of the shape, you identify one specific boundary line. The side directly opposite the 90-degree anchor is the hypotenuse, labeled here as h. The hypotenuse is an absolute constant. Its identity is locked to that 90-degree angle and remains the same regardless of how the triangle is rotated or flipped. Solving for a triangle requires identifying this permanent side before calculating the variables that change. Once the absolute is established, we can look at the remaining two acute angles. These act as two distinct observation points. Notice angle A. If chosen as our focal point, the opposite side is the perpendicular, and the adjacent side is the base. Shifting observation to angle C demonstrates relativity. The base becomes the perpendicular, and the perpendicular becomes the base. Throughout this shift in perspective, the hypotenuse remains unaffected. The definitions of base and perpendicular depend entirely on the observer's chosen frame of reference. We have three lengths: the perpendicular, the base, and the hypotenuse. The next step is to determine how they interact structurally. This shows the logic binding them. Perpendicular squared plus base squared equals hypotenuse squared. The Pythagorean theorem acts as a rigid constraint. Knowing the length of two sides mathematically reveals the third. When analyzing a triangle, if two variables are provided and one is missing, this formula is the mandatory first step to resolve the system. No single side can change its dimension without forcing a proportional adjustment in the others. The triangle operates as a deterministic mathematical engine. Beyond measuring side lengths, we can analyze the proportional relationships, or ratios, between those sides. We have a restricted data set, the variables p, b, and h. The goal is dividing one variable by another to create a unique ratio. Combining these into two-part fractions yields exactly 6 unique combinations. The existence of 6 core trigonometric functions is a combinatorial certainty based on these variables. We simply assign formal, standardized names to these 6 inevitable mathematical combinations. Dividing the perpendicular by the hypotenuse gives our first combination. We assign it the title sine. The second divides the base by the hypotenuse, named cosine. The third divides the perpendicular by the base. We title this tangent. Sine, cosine, and tangent are shorthand titles for the 3 primary ways to measure these sides against one another. That covers the first 3 ratios, leaving 3 remaining combinations to complete the set. These final 3 ratios are symmetrical reciprocals of the primary 3, found by inverting previous fractions. When sine, p over h, is flipped to h over p, it is called the cosecant. Cosine inverts to hypotenuse over base, labeled the secant. Tangent inverts into base over perpendicular, named the cotangent. This logic organizes 6 functions into 3 pairs. Recognizing this symmetry reduces the need for rote memorization. The list is a balanced mathematical mirror. We have now derived the complete set of trigonometric ratios. This dashboard maps how these 6 ratios wrap around the triangle. Changing the focal angle cascades through this matrix, altering values without breaking the logic. And the Pythagorean theorem remains the foundation, calculating these ratios even with missing data. There are no hidden variables in this basic geometry. The system is exhaustive and complete. Trigonometry operates as a closed-loop system, defined by 3 sides, guided by one formula, and 6 formal proportional names. Deriving the system from first principles proves why these rules exist, replacing rote memorization. The process begins with the absolute, unchanging nature of the hypotenuse. It incorporates the fluid relativity of the base and perpendicular, which are strictly defined by the observer's chosen position. Logically combining these variables yields exactly 6 unavoidable proportional ratios. This overarching framework provides us with a truly systematic way to precisely quantify the intricate geometric properties of our physical space.